Hello friends, welcome back to my YouTube channel. In this fifth part of my discussion on liquid extraction, I will be discussing how to plot the binodal solubility curve and the distribution diagram. So we are going to understand the plotting of these two diagrams with the help of a simple example. So you will learn how to use a triangular graph for plotting the binodal solubility curve, and then how can we use the equilibrium data to plot the distribution diagram. So basically I will be discussing one numerical where we will be plotting the binodal solubility curve on a triangular graph. In this you will learn how to use the triangular graph, and then on a simple rectangular plot we will be plotting the distribution diagram. So what is a binodal solubility curve, and then what is the distribution diagram? I have already discussed it in my previous video, that is liquid extraction part number 4. I'm giving link to that video and other relevant videos, other earlier videos on my on the topic liquid extraction. So let us start the discussion. Okay, so first let us look at the numerical statement. The Turner equilibrium data for the system of water, which is denoted by A, isopropyl ether, which is denoted by B, and acetic acid, which is denoted by C. It is given in the table. I will shortly show the table to you. And by using this equilibrium data, we are supposed to plot the binodal solubility curve and then the distribution diagram. Simple task. From the given ternary equilibrium data, we will be plotting the binodal solubility curve on a triangular graph, and then we will be plotting the distribution diagram on a rectangular graph. So let us plot the two curves. Okay, now let us look at the equilibrium data, the data that is given to us, Turner equilibrium data. So in this table you have information about two layers: water layer, which is water rich layer, and then isopropyl ether layer, isopropyl ether rich layer. So why we call this as water rich layer? Because you can see the major component is water, in this case E, because we have denoted water by E, so major component is water. So that's why we are calling it as the water rich layer. And this is isopropyl ether rich layer because the major component is isopropyl ether. We have denoted isopropyl ether by B, so the major component is B in this case. So that's why it is isopropyl ether layer. Okay. So this information, the information in this table is applicable, or the information is for the case when these two layers are in equilibrium with each other. Water rich layer is in equilibrium with isopropyl ether rich layer. So all these are equilibrium compositions. So that's why it is the Turner equilibrium data, and we are going to use it to plot the binodal solubility curve and then the distribution diagram. Okay, so first let us list what is given to us, the given data. So you have a ternary system of three components: water, that is A, isopropyl ether, that is B, and acetic acid, that is C. The ternary equilibrium data is given to us, and what are we supposed to do? first we have to plot the binodal solubility curve, and then we have to plot the distribution diagram. Simple task. Okay, now let us go for the solution. So first we will plot the binodal solubility curve, and for that we are going to use this information. So the ternary equilibrium data that is given to us. So it is given in percentage. So this is percentage of A, percentage of B, and then percentage of C in water layer. And then you have percentage of A, percentage of B, and percentage of C in the isopropyl ether layer. Okay, so we are going to plot, as I said earlier, we are going to plot the binodal solubility curve on a triangular graph. So I'll show the triangular graph that I'll be using over here. So this is the triangular graph that I'll be using, and we are going to plot this ternary equilibrium data on this triangular graph. So this apex I'm going to denote, or this apex, let it represent pure component A. This apex, let it represent pure component B, and this apex, let it represent pure component C. So composition of A in the mixture of the three components A, B, and C, it will be given by these lines. So for example, let us say you have this line, 10% line. On each side is representing percentage composition. So you have 10%, 20%, 30%, so on and so forth. Same is the case for the remaining three sides. Each side is representing a binary mixture. For example, side AB is representing a binary mixture of A and B. Side BC will be representing a binary mixture of B and C. And side AC will be representing a binary mixture of A and C. Now, at any point within this triangle would be representing a ternary mixture. So for example, let us consider this line, a line of 10%. So what does that give? What is the significance of this line? This line, or along this line, the mixture will be containing 90% of A in it. So percentage of A will be the perpendicular distance of a point on this line from the side BC. So this line, if you consider a point, for example, this point. So this point is representing, and I have considered a point on the 10% line. So this point, any point on this line, it will be representing a ternary mixture which will be having 90% of A in it. So I have talked about how to use the ternary graph, equilateral triangular graph, in my earlier video. I am giving link to that video in the description section. Similarly, say any other point. Let us talk about C in the mixture. So for that, if I consider this point, now where is this point? This point is on the 20% line. And if I have to report the amount of C in it, so it will be equal to the perpendicular distance of this point from the side AB. So in this case, it would be containing 20% of C in the mixture. And for B, we have to consider this lines. So for example, if I consider a point on the 70% line, so this point, or any point on this line, it will be giving the percentage of B in the mixture. So this point, it will be giving percentage of B in the mixture of E and C. So this point, at this point or any point on this line, it will be containing 70% of A in the mixture. 70% of A in the mixture of A, B and C. So this is how you have to plot compositions of each component in the mixture, and we are going to use the same technique for plotting the binodal solubility curve. So these lines, that is lines parallel to the side BC, will give percentage of A in the mixture. Lines parallel to the side AC will give percentage of B in the mixture, and lines parallel to the side AB will give percentage of C in the mixture. So we are going to use this concept for plotting the binodal solubility curve. So let us go ahead. First, let me erase. I hope you have understood how the points are to be plotted. If you have any doubt, you please mention that in the comment section. Let us start with. So what we will do, we will plot a point. For example, the first entry, 98.1% of A, 1.2% of B and 0.69% of C. So we have a mixture that contains 98.1% of A, 1.2% of B and 0.69% of C. So this mixture in the water rich layer is in equilibrium with a mixture that is containing 0.5% of A, 99.3% of B and 0.18% of C in the isopropyl ether rich layer. So let us simultaneously plot those 2 points. Let us first plot this point, a mixture that is containing 98.1% of A. So this point will be lying over here. So the first line from apex A, first line parallel to the side BC from apex A will be representing 98% composition. For example, each division, it represents 2% composition. So for example, this is 10, so this is 12, 14, so this is 10 and this is 10, 12, then you have 14, 16, 18 and 20. That is each small division on this particular graph represent a composition of 2%. So you can use a different scale, that is not a problem. I have used that scale, the scale where one small division is equal to 2%. So in that way, 98.1% of A in water rich layer, it will be represented by this point, the point that is lying on a line close to the line of 98%, which will represent 98.1%. And then the mixture is containing 1.2%. So we have to consider a line that is parallel to side AC to represent composition of B in it. And this, since it is containing 1.2%, so this point is lying over here. So the first line from side AC will represent 2% of B in the mixture, and we have to represent a composition of 1.2%. So accordingly, the point is placed over here. So if you fix the composition of 2 points or 2 components, the composition for the third component will be automatically fixed. For example, in this case, percentage of C in the mixture is 0.69. So you can see we are talking about a line that is parallel to side AB. That means in order to represent percent of C in the mixture, we have to use lines that are parallel to the side AB. So in this case, the point over here, it is below the first line that is parallel to the side AB, and that is approximately representing 0.6 line. So if you fix the compositions of two components, the composition for the third component will be automatically fixed. Now let us plot this point. This mixture is going to is containing 99.3% of B in it. So now we are going to use lines that are parallel to the side AC for representing composition of B. I hope you are understanding it. So 99.3% of B, it will be represented by a point that will be lying in front of the 98% line for B. Okay, so these 2 points, the 2 points or the compositions represented by the 2 points, they are equilibrium compositions. So likewise, all other points have to be plotted by using the same technique. So the second point is now plotted over here. The third point is plotted over here. Then the fourth point, I am simultaneously plotting. Fourth point, it is 91.7 of E. So it will be coming over here. So sorry, the fourth point is, the third point over here is 95.5% of E. So likewise, it will be represented in this way. Then the point, the next point is 71.1. So the point is represented over here. Then the corresponding point is represented on the side. So this composition is in equilibrium with this composition. This composition is in equilibrium with this composition. And this composition is in equilibrium with this composition. So in this way, you get the points for water rich layer and then points for the isopropyl ether rich layer. So you have point 1 representing 98.1. Then you have the point that is representing 97.1. And then you have 95.1, the third point, 95.5, third point, and fourth point is 91.7, 91.7, and the other point is, say, 91.7. So this will be 90. This is the fourth point, 91.7. Then next point is 84.4. So it will be represented over here. Then you have 71.1. 71 point. Let us go point by point. The first point is 98.1 over here. The corresponding point, 99.3% of B, is represented over here. Then the second point in this is 97.1, and that is represented over here. Third point is 95.5, so it is represented over here. Fourth point is 91.7, it is represented over here. And likewise, then you have 84.4, this point is represented over here. 71.1, this point is represented over here, 71.1. And then you have 58.9, it is represented over here. And then you have 45.1, it is represented over here. And then 31.7, it is represented over here. Likewise, in the same way, compositions in the isopropyl ether rich layer, they are presented by all these points. Now, in order to get the binodal solubility curve, we are going to draw a smooth curve through all these points, and that curve will be nothing but the binodal solubility curve. So this is the binodal solubility curve. I hope you have understood how to plot all these points. And then one more task we are going to carry out, and the task is we will be joining the corresponding points. So point representing this composition will be joined to the point that is representing these compositions. And you know, the line which joins compositions that are in equilibrium with each other, we call them as a tie line. So I'm going to draw all those tie lines. Tie lines are connecting equilibrium compositions, composition in the water rich layer and composition in the isopropyl ether rich layer. So all these are tie lines. All these are tie lines. The concept of tie line I have discussed in my previous video on binodal solubility curve. I'm giving link to that video. You please watch it. So in this way, you have to plot the binodal solubility curve on the triangular graph, equilateral triangular graph. I hope you have learned how to plot these points, how to plot or how to use the triangular graph to plot the binodal solubility curve. Okay, so after plotting the binodal solubility curve on a triangular graph, now let us plot the distribution diagram. So distribution diagram, it will be plotted on a rectangular graph. For this, we need to convert this data in order to get x and y. The conversion is simple. What is given to us is percentage. We want weight fraction. These are weight percentage, weight percentages. Okay, and we want to have different values of x. What does x represent? X represent weight fraction of C in the mixture. What we have is the weight percentage of C. So in order to convert weight percentage of C into x, we will have to simply divide the percentage value with 100. So in this way, you can get all x values. So this percentage is divided with 100. So in this way, you get all the weight fractions for C in the water rich layer. Similarly, in isopropyl ether layer, we are going to list y values. What is y? Weight percentage of C, weight percentage of acetic acid. Sorry, weight fraction. Y represents weight fraction. So y is weight fraction of C in the isopropyl ether layer. And you have percentage of C, weight percentage of C. So divide it with 100, you get y. So this will be, I'm just now showing you the values of y which are obtained by dividing the weight percentage with 100. Now the task is we have to plot x versus y on a rectangular plot. And the resulting diagram will be the distribution diagram. The curve obtained will be the distribution curve. So let us the curve plot. So on this, I have collected all y values, x values, and then all y values. I'll be using a simple rectangular graph where x will be plotted on the x-axis and y will be plotted on the y-axis. And then for reference, I'm drawing a diagonal line. And if you plot the given data, you'll be getting a curve. And now you can see the curve that is obtained in this case, it is lying below the diagonal line. So it can happen that the curve may be lying above the diagonal line, but for the present data, the curve is lying below the diagonal line, which confirms that in this case, C is favoring A. That means composition of C or weight fraction of C in the water layer is greater than weight fraction of C in the isopropyl ether layer. That's why the curve is lying below the diagonal line. If the curve was lying above the diagonal line, then the case would be C is favoring B. For this case, C is favoring A, and that's why the curve is lying below the diagonal line. And what is this curve? This curve is nothing but the distribution curve. This is the distribution curve. And the diagram that we have drawn over here is the distribution diagram. So in this way, you can plot the distribution diagram. So the Turner equilibrium data, you can convert to the data, that is weight fractions of C in the water rich layer and isopropyl ether rich layer, and then you can plot X and Y values to get the distribution diagram. So in this way, I complete my discussion for this video, and my objective was to tell you how to use the triangular graph for plotting the binodal solubility curve, and then how to use the Turner equilibrium data to plot the distribution diagram. I am sure and I am hopeful that you have understood how to plot the two diagrams. So with this, I end my discussion for the present video. Thanks for watching the video, and do subscribe to my channel. Tell your friends to subscribe to it, and don't forget to hit the bell icon so that you'll be notified as soon as I upload any new video on my YouTube channel. For now, thanks and bye bye.